Good day everyone. Welcome to Unit 5 Lecture 4 for CpE 2301 Logic Circuits and Design. Unit 5 Lecture 4 covers the discussions about clocks and clock generators, frequency division, and counters as frequency dividers. To begin our discussion, let's first define what a clock or a clock generator is. A clock or clock generator is an electronic oscillator that produces a clock signal for use in synchronizing a circuit's operation. The signal can range from a simple symmetrical square wave to more complex arrangements. These characteristics of a clock make it an essential component in the operation of sequential circuits. A clock generally has no inputs, but generates a single output. The output, as mentioned, aid in the timing and synchronization of sequential circuits. Clocks are often defined and characterized according to the following: their frequency, their period, their duty cycle, and magnitude or amplitude. We will discuss these terms further in a while. Frequency refers to how often a particular task is performed per unit of time. With regards to a clock or clock generator, frequency refers to how many periods it could generate per unit of time. Frequency can be mathematically expressed as 1 over period or 1 over t. T here is again the period. The unit for frequency is Hertz, which can be abbreviated as just Hz. Hertz can also be interpreted as cycles per second. That means 1 Hertz is equivalent to 1 cycle per second. Period, on the other hand, can be mathematically expressed as 1 over frequency, or 1 over f, where again, f is the frequency. The unit for period is seconds. You can see from their mathematical expressions that frequency and period are multiplicative inverses of each other, or simply reciprocals. So we can better understand frequency and period, let us take a look at a sample clock signal. The clock signal we have here is a periodic signal. A periodic clock signal is simply a signal that repeats a specific pattern as seen here in the waveform. Looking at a clock signal, period can be defined as the amount of time it takes for a periodic clock signal to output one repeating pattern. Therefore, we can simply locate a portion of the signal and look at how much time it needs to repeat that part of the signal in a pattern. For this signal, we can have the following examples. From the labels on the signal, we used T to signify period. We can see that this part of the signal repeats at this point and repeats again at this point. If we take another part of the signal, like this point, it repeats at this part of the signal. If we take other points of the signal, you will see that the time it takes for them to repeat the signal pattern is uniform with any other points of the signal, as shown by this and this. So that is how period can be illustrated in a periodic signal. To relate this to frequency, frequency simply refers to how many contiguous periods there are in 1 second. Amplitude of a signal simply refers to this magnitude as shown by the height of the signal. The Hertz unit of frequency can be attached with a prefix like kilo, mega, giga, or tera to signify 1,000, a million, a billion, or a trillion, respectively. They can be written as the following, where 1 kilohertz means 1000 hertz, 1 megahertz means 1 million hertz, 1 gigahertz means 1 billion hertz, and 1 terahertz means 1 trillion hertz. Since frequency and period are reciprocals, the unit of time per period are the following: 1 millisecond for 1 kilohertz, 1 microsecond for 1 megahertz, 1 nanosecond for 1 gigahertz, and 1 picosecond for 1 terahertz. When it comes to clock signals, one of the most commonly used in sequential circuits is the square wave signal. Square waves are symmetrical and have equal duration for high or 1 and low or 0 parts. That means, for example, if we take this point until this point as one period, it means that half of the period the signal is high or 1, and half of the period the signal is low or 0. Given that, we can consider a square wave to have 50% duty cycle. That means 50% of the period the signal is high. If you look at the diagram here, we have a term called pulse width, which simply refers to the part of the period where the signal is high or 1, just like this part. This edge part of the signal, where the transition from low to high occurs, is called the rising edge, or leading edge, or positive edge. This edge part of the signal, where the transition from high to low occurs, is called the falling edge, or trailing edge, or the negative edge. Let's try to solve an example. A square wave waveform has a pulse width of 10 milliseconds. Calculate its frequency. It is mentioned in the problem that the signal is a square wave, which means that it has a 50% duty cycle. It is also mentioned that its pulse width is 10 milliseconds. Given that, we can say that the entire period of the square wave is twice that of 10 milliseconds. If we have the period, we can easily get the frequency, and so our solution will look like this. The frequency for the square wave waveform is 50 Hz. Clock signals do not always have 50% duty cycle. Sometimes, in a clock period, the pulse width for the positive half and the negative half are unequal. They are called rectangular waves and may look like this. To get the duty cycle of rectangular waves, we can use this equation. Duty cycle, or DC in this equation, is equal to the pulse width divided by the period times 100%. Always remember that duty cycle is measured in percentage. And again, the pulse width here refers to the amount of time in a period where the signal is high or 1. Duty cycle can be used to regulate the amount of power being applied to a load such as a lamp or a motor by varying the duty cycle of the waveform. Varying the duty cycle will increase or decrease the light intensity on the light or lamp and the speed of the motor rotation. The process of varying the duty cycle is called pulse width modulation. Let's try to solve an example. A rectangular waveform has a pulse width of 20 milliseconds and a total period of 50 milliseconds. Calculate its duty cycle and frequency. From what is given, we can easily get the duty cycle since we know the signal pulse width and its period. The solution will look like this. The duty cycle of the rectangular waveform is 40%. In the same manner, we can also easily get the frequency because we know the period. And so the solution will look like this. The frequency of the rectangular waveform is 20 Hz. The frequency of clock signals can be divided. That means when your circuit needs a low frequency signal, but the available clock signal you have is high frequency, you can create a circuit that can divide or reduce it to the required frequency. Here we have examples on how to divide frequency. D or T flip-flops can be used to divide the frequency by 2 when they are connected in this manner. Let's say, for example, that this is a clock signal that you want to divide or decrease. If you input this clock signal to the flip-flop clock inputs here and here, the clock output frequency taken from the D flip-flop here and the T flip-flop here will be divided by 2, which will now look like this. What happens on the D flip-flop is that every correct edge detected at the clock input In this example, the rising edge, as shown by this upward facing arrow, the Q bar or inverted output of the flip-flop is taken as input back to the D flip-flop input and shall be shown at the output. In this manner, the output here would simply shift high and low continuously every period or rising edge of the input clock signal, thereby dividing the clock output signal by 2 in terms of frequency. And again, the output frequency will look like this. What happens on the T flip-flop is that every correct edge detected at the clock input, in this example again, the rising edge as shown by the upward pointing arrow, the output here would simply shift high and low continuously since the T input is high for the T flip-flop. And it would happen for every period or rising edge at the clock input signal. So thereby dividing the clock output frequency by 2. And again, the signal waveform of the output will look like this. Another way to perform frequency division is to use counters. Just like what was previously mentioned, the division process is used to reduce a frequency to a more usable value and are often used for time-keeping devices like digital clocks. To create frequency dividers using counters, counters are formed by cascading flip-flops together to form a modulo n counter, where n is the number of output states or counts. With that, a modulo n or mod n counter is also called a divide by n counter. This means that in order to divide a given frequency by, let's say, 16 for example, you have to create a modulo 16 counter. The most fundamental frequency divider is the binary ripple counter. Here we have an example of a modulo 16 counter. It is simply made up of 4 flip-flops given by this, and this. The output of this flip-flop, labeled as QA, is the least significant bit, and the output of this flip-flop, labeled as QD, is the most significant bit. What happens is that if we put this clock signal to the clock input of this flip-flop, the output taken from the flip-flop here is divided by 2 in terms of frequency, as shown by this waveform, the QA waveform. The clock output taken from this flip-flop, as shown by your QB, will be divided by 4, as seen in this waveform labeled as QB. The clock output taken from this flip-flop here, labeled as QC, will be divided by 8 in terms of frequency, as shown by the waveform here labeled as QC. And finally, the clock output taken from this flip-flop shall be divided by 16 in terms of frequency, as shown by this waveform labeled as QD. As you can see, the 1 cycle or period in the final output frequency takes the same amount of time as the 16 cycles of the original input frequency. Thus, the input frequency has been divided by 16 using a modulo 16 counter. Using the modulo 16 counter, we can have a 100 kilohertz frequency, for example, and then we can get the following frequencies after frequency division. 50 kilohertz after dividing by 2, 25 kilohertz after dividing by 4, 12.5 kilohertz after dividing by 8, and finally 6.25 kilohertz after dividing by 16. The disadvantage of using ripple counters in frequency division is we are limited to dividing them by 2 to the n. That means you can only divide by 2, 4, 8, 16, 32, and so on and so forth. In order to perform specific frequency divisions, you can create modulo n counters using various implementations. Here, for example, you can create a modulo 6 counter using counter ICs to divide, for example, a 60 kilohertz to 10 kilohertz, or create a modulo 10 counter using counter ICs to divide the 60 kilohertz and generate 6 kilohertz output. These implementations can be used for other similar frequency division applications. So that ends this lecture. Thank you for watching and listening, and have a good day.